This is Statistics 243 at UC Berkeley for Monday, November 17th.
Yeah, we can just say like do a drawing. Yeah, we can just give like suggestions.
Alright, let's go ahead and get started. Okay, so we're going to switch over to multivariate optimization, which is of course usually the real problem that we need to solve. And so what we'll see today and on Wednesday is some of the connections between different names that different kinds of multivariate optimization go by. And we'll see that a lot of them are very closely related, and a lot of them are very closely related to doing Newton-Raphson, or Newton's method. But before we get to that, a sort of core technique for when you're doing optimization is to see if you can analytically maximize over some of the parameters or some of the coordinates in the vector that you're trying to optimize with respect to. So I guess I didn't say this before, but hopefully it's obvious and hopefully it was clear anyway. You know, if we have a problem where I can just take a derivative, set it equal to 0, and then solve for the vector of interest, of course we would do that. That would be an analytical optimization, and we wouldn't be doing all of this numerical stuff. The problem is that most times, or many times, we can take that derivative, but we can't then set that equal to 0 and solve in closed form mathematically for the parameter or parameters of interest. So the idea of profiling is it might be the case that you could, in some subset of the dimensions, some subset of the coordinates, some subset of that vector of parameters, analytically maximize with respect to that. That's going to take your larger dimensional space and get it down to a smaller dimensional space, and then you would maximize in the smaller dimensional space. And the reason for doing this is that as the dimension of the space gets bigger, it's much, much harder to do the numerical optimization. So anything you can do to get the dimension of that space smaller to start with is going to be really helpful. So that's what in statistics goes by the name of profiling, particularly when it's applied to maximizing a likelihood, and then we'll start talking about a profile likelihood or maximizing the profile likelihood. So you can imagine that you might have a picture something like this, and I'm just going to do it in 2 dimensions, but the idea is this will generalize to higher dimensions. So suppose you're trying to maximize with respect to theta 1 and theta 2, and this is the, say, log likelihood surface that you're trying to maximize over. And so maybe the maximum is right in here. Well, the idea is that if for any given fixed value of theta 1, if I can analytically maximize with respect to theta 2, we can sort of think about what the picture looks like if I do that. I pick a value of theta 1 and I maximize just to do this one-dimensional maximization. Of course, if I were doing this more generally, this would be a higher dimensional maximization. And I say, oh, okay, that's the maximum there. And then I do it for another value of theta 1, and I say, oh, that's the maximum there, and I continue onwards. And if I do this for every value of theta 1, then I have this curve, which is this is basically the profile likelihood. Okay. And now I can basically now I basically have theta 2 hat as a function of theta 1. So I basically analytically gotten maximized out. I don't know if that's the right wording. But I basically analytically removed theta 2, and now I just have to do my numerical maximization with respect to the remaining theta 1. And if I were to plot this as the profile likelihood, so here I've got the likelihood or log likelihood is sort of coming out of the board at us in this 2-dimensional space over which I'm optimizing. But if I think about having done this profiling, I can now think about, well, let's say the log likelihood of theta now as a function of theta 1, and that will look like sort of whatever the values are along this curve as a function of theta 1. So however far out of the board they're coming. So maybe in this case, that would look something like this, where this value here is supposed to line up in the same place that it lines up here in this picture. Okay, so any questions about the big picture there? Okay, so I thought we could just see, I won't go through every single step because this is a fairly simple problem, but I thought we could just see this in a concrete example here, this is basically sort of a weighted least squares problem. So suppose you had the following regression model. You just had a standard linear regression on of y on x here, but instead of having IID random errors that would just be the sigma squared. I instead have some matrix sigma that's, say, a function of a single parameter rho. And so suppose this might be a model where I've got where my errors are autocorrelated, say, over time. And so maybe I have x1, x2, x3 on up to xn. And rho says something about how autocorrelated the, sorry, I shouldn't have used, used x there because that's going to get it confused with the covariates. Suppose I have y1, y2, y3 up through yn, and I have an error epsilon, epsilon1, epsilon2 up through epsilon n. Those epsilons might be autocorrelated in this sort of sequence that I'm talking about, which might be time itself. And so if I did that, I might have a model that says, oh, I think that the errors, and this is the covariance of those epsilons, of those errors, has some correlation structure, and I'm going to parameterize that with this sigma matrix. But that sigma matrix is going to have rho in it, and rho is going to be my unknown parameter. So questions about the setup here? Okay, so now if I think about this, what do I have in terms of the parameter space? I have a sigma squared, I have the rho, and then I have as many betas as there are in this beta vector. Okay, so this could be a fairly high dimensional optimization. Okay, so the idea is if I write this down, well, if I look at this, I'm like, well, okay, the part that involves beta shouldn't be very hard to deal with because that just looks like sort of a standard linear regression. And if I know something about using generalized least squares, I actually sort of already know the answer to the problem just for finding beta. So I would start by writing down what the likelihood is. So this is just the multivariate normal likelihood. Where I'm indexing, where I'm saying that I put this little rho under the sigma to indicate that there's just, say, a rho involved in the calculation of the sigma. And now if I take the log, well, okay, I get this log likelihood. And now I could think about the fact, well, probably if I differentiate with respect to beta, set that equal to 0, I can probably solve for that in closed form. Okay, so I can take the derivative of this log likelihood with respect to the beta vector, and I won't work it out, but this is quadratic in beta. So if you just work through the derivatives in terms of the matrix derivatives with matrix vector notation, then what you'll do that differentiation, set it equal to 0, solve for beta, and then you get that beta hat is whatever I wrote down. Did I write down somewhere here? Yeah, beta hat of rho, and I'm denoting it as a function of rho there because if we write down what it is, then it looks like this is just a generalized least squares estimator for those of you who've seen this before. And so we've got x transpose sigma. I guess I'm switching back and forth in my notation between a subscript rho and having it as a function of rho. I don't mean anything substantively by that. Okay, so this thing is obviously a function of rho because I still have the sigma in the problem. But now I can say, well, I've now basically done what I said here, is that for any given value in one of the dimensions, I'm going to maximize with respect to one of the other dimensions. And then I'm going to get, in this case, I got my sigma, my theta 2 hat as a function of theta 1. Here I got my beta hat as a function of rho. So now I can just do the next step here, which is just plug this beta hat of rho back into my log likelihood. Okay, so now I'm going to have L is equal to, I'll put a little p on it to indicate this is now a profile log likelihood. So I still have sigma squared. Nothing has changed in terms of that. I still have the -1/2 log of sigma. And then I have -1/2. But now I'm going to have y minus x beta of rho transpose sigma of rho. Sorry, I keep changing that. Over sigma squared. Okay, so now I've gotten this already down to a two-dimensional optimization, so I've already made quite a bit of progress in terms of reducing the dimensionality of the problem. And now if I look at this, and if I've ever worked with a regression likelihood before and just found the maximum likelihood estimate for regression, I'll probably recognize, oh, if I just take derivatives with respect to sigma squared and set that equal to 0, I'm going to be able to also solve for sigma squared. And then I'm just going to have rho left in the problem. So once I go ahead and differentiate with respect to sigma squared and solve that, then I get this equation here, which is basically, if you look at it, it makes sort of sense. This looks like a maximum likelihood estimator. Like this is the usual maximum likelihood estimator for an error variance. It's just a sum of squares. If I ignore this part, it's just the usual. It's just a residual sum of squares divided by n. So that's just a variance estimator. But in this case, there's this adjustment that has to take account for all the correlation structure in the errors. So okay, now I have a profile. Now I have my profiled estimate of sigma squared. Of course, it still also involves rho. So the problem's not done yet because of course I don't know what rho is, what my best value of rho is. But if I now take this value and now plug that into sort of my currently profiled log likelihood here, and just plug in the sigma squared hat here and here. Well, now the sigma squared hat gets plugged in there. You'll notice the y minus x beta, sigma inverse y minus x beta, that's just the same thing that's up here in the numerator, so that's going to cancel out. It's actually going to work out quite nicely. And at the end of the day, once I've written out this sort of next level of doing the profiling, I end up with this equation here. So now, probably it's the case that I'm going to have this matrix that's a function of rho. It's probably, if I start taking derivatives of the matrix with respect to rho, I'm just going to get some other matrix that has somehow derivatives with respect to rho, and it's going to be hard to then deal with that and set that equal to 0 and solve for rho. So now at this point, I would presumably resort to just doing numerical maximization of this. In this particular problem, this is now a univariate maximization, which is really, really easy. It might take a while to solve because I suspect there are going to be, if this is a big matrix, there are going to be then I'm going to have to. This is going to involve some perhaps a fair amount of computation. But in terms of the optimization problem itself, it's not a hard optimization problem. And so then what do? Once I get my best value for rho, I can then go back in, plug in, and find my best value for beta hat up at the top. I can plug that in here, and then calculate this, and then I can find my best value of sigma squared, and I'm done. I've got all three of the components of my parameter vector that I'm interested in finding. So that's often a nice strategy if you're in these situations where it's possible to do it. And oftentimes we are working with a model that is sort of potentially just a more complicated version of some simpler model that we're sort of familiar with, like in this case. And we might actually already be sort of familiar with the kinds of manipulations we would do to try and to take derivatives and work with those. Okay, so any questions about that? Okay, so that was this sort of a preparatory step of once you've got the problem you need to optimize, look at it and think about it and see if there's anything you can do analytically that will make the problem easier. Now we'll assume we're on to the stage where we know we have to do something numerically. So if we think about taking Newton's method and modifying it for the multivariate setting, it's not really any different, except now we're going to be working with vectors and matrices. So remember that our original Newton-Raphson update looked like this, where I had the current x in my iterations. I subtract off the inverse of the second derivative and multiply that by the gradient. So if I now basically do the same kind of derivation with doing a Taylor expansion and an approximation and thinking about following down, the gradient, except in this case a gradient vector, what I find is that the Newton-Raphson update is now, I've got minus, and now I have the inverse of the Hessian matrix, so the inverse of the matrix of all those pairwise partial derivatives, second derivatives. And then I have my gradient vector here. Okay, so there's not, so in some ways it's not all that much more complicated than what we've already seen in the univariate case. Obviously, if we're taking a derivative here, we need to worry about whether or not this matrix is going to be is always going to be positive definite. So whether doing an inverse, whether that matrix is positive definite. So I could actually solve the implied system of equations that's going on here with the inverse times the vector. I have to worry about calculating all these derivatives and making sure I don't have a bug in my code that calculates the derivatives. We sort of mentioned that last time. And the usual story with going to higher dimensions just makes it harder in terms of Newton's method of making sure that I'm not going off to some other local minimum instead of the global minimum, or that I'm not going off to a local maximum instead of the global minimum, or that I don't have these problems where I sort of diverge away from the solution instead of narrowing in, zooming in on the solution. Okay, so I thought we could look at an example of just using Newton's method for a fairly simple problem. So this is the model that I'm going to fit, and I believe these are. Actually, I should have looked this up more carefully because I haven't looked at these data in a while. I believe these are data that are basically looking at weight loss in, I don't remember if it's a human or an animal or somebody, but y is weight and t is time, and so the idea is to sort of create a regression model that basically fits the decline in weight over time, and the idea was to fit this nonlinear function. So this is a function where we have an intercept and a regression coefficient, but sort of inconveniently from the perspective of finding the maximum likelihood estimators, we have this beta 2 up in the exponent of the sort of what you can think of as the covariate here. And so that's going to make this thing hard to maximize or minimize the negative log likelihood numerically. Okay, so let's go ahead and look at, let's see some R code to do this. Okay, so this is the weight loss data that's in the in this MASS package in R. And so here it is. We're just going to plot it out and see what it looks like. So it looks like there's sort of some curvy nonlinear behavior here in terms of the amount of weight over the number of days. I hope that's not a person, because that looks like a fairly extreme weight loss. Maybe it's unhealthily fast. I don't know. What's that?
What animal was that?
Well, I guess that's the other question. I don't know. So maybe it is just a person. Okay, maybe there's probably some help information in the weight loss example, in the weight loss object if you do help on it. So just sort of to motivate this, if we fit a linear fit if we do a linear fit on this. On these data, and just fit a linear regression as a function of time. Sorry, this color is terrible. All right, so I won't bother replotting it, but there's a very, very thin gray line, straight line running down here that obviously doesn't, it sort of fits the data, but it doesn't really capture the curve, the nonlinearity in the observations very well. Okay, so part of the reason, this is a pretty simple example, but part of the reason I wanted to go through it is just to start to develop some ideas of how would we come up with starting values, and how could we look at the structure of a given model and think about what are sort of plausible starting values. And so you could sort of think of this from two perspectives. One is it would be great to get really, really good starting values if you had some good way of doing that. But the flip side of that is maybe all you need to do is make sure you don't have really terrible and stupid starting values. And as long as you start sort of somewhere that's sort of not too bad, you may do fine. So if we go back and look at that, if we go back and look at this, sort of the difficult part of finding starting values here is these just look like coefficients of linear regression. So those are probably going to be pretty easy to deal with. But the question is sort of what even scale should I use for the beta 2? And so should that be something like 1 or 10 or 100 or a million or a zillion? If you don't sort of think about it a little bit, you might not know. But one thing that often happens if you're thinking about these sorts of scaling kinds of things, where I'm dividing some, say, these are sort of like covariates of time here, divided by a coefficient, is you might just want to think about, well, what's the order of magnitude of the time values? And that might tell me something about what the beta 2 value should be. So in this case, I just said, well, if I look at this days value, maybe the fact that days is sort of has an order of magnitude of around 100 suggests that maybe that means the beta 2 should be something like 100 or so. And so that was sort of my first idea of like, oh, let me just make sure it's sort of, that might give me an indication of the order of magnitude. And so then I said, well, if that's the case, 2 to the minus time over beta 2 is basically my new covariate. If I knew beta 2, I just have a regular regression covariate. So that's what this is. I'm sort of creating an x based on some initial guess at beta 2, and then I'm going to see how it relates to y and see if it looks like there's a linear relationship. Because if I've got the beta 2 right, then if I've got sort of a reasonable beta 2, then I should just be able to see that y is linear related to 2 to the minus t over beta 2. Okay, so sort of just looking at the structure of the problem and thinking about what sort of diagnostic plots I could do to make some headway here. Okay, so here's what happens if we do that. And we can see that it doesn't look too bad. If I now think about this as a regression of y on this sort of derived x variable, again, that looks sort of linear. Right? So maybe I'm not doing too badly. I could try out different values of beta 2 and see how they go. Like what if I did 1,000? Would that look terrible? Would that look okay? Okay, so that sort of looks more curvy than with beta 2, trying an initial value of 100. What if I tried out 10, so you could just sort of play around with this sort of thing? Well, that's pretty bad, right? So that's sort of an indication that 10 is not the right order of magnitude for this this particular covariate. Well, okay, so let's go back to 100 since it seemed like that was pretty good. Okay, so how do I get my so now I have I have a potential starting value for beta 2. How do I get starting values for beta 0 and beta 1? So Guanzheng, any ideas? So what does this look like? If I tell you what beta 2 is, what can I do? Kelly?
So you're trying to figure out beta naught and beta 1?
Yep.
Beta naught should just be the intercept, right?
Yep.
And then beta 1 would be like the slope of that line, and you would use the value of beta 2 that you guessed right now, and work
Yeah.
with
So
that.
right. So once I have a beta 2 that I've made a guess at, this is just a regression. I could just fit that regression with the given beta 2 and come up with a beta 0 and beta 1. Now it's not going to be the true beta 0 and beta 1 because I don't have the true beta 2 unless I got really lucky. It's going to be the beta 0 and beta 1 that are consistent with my starting value for beta 2. Okay, so if I go ahead and do that, that's exactly what I'm writing down here. So this is going to do that regression and get my initial values for beta 0 and for beta 1. So now I have a beta 0, beta 1, and beta 2. I'm just going to go ahead, in this case I can just make a plot. This is, the red line is if I take the beta 2, the beta 0, and the beta 1 and we just talked through, and I use those and I just show the fitted, and I just show the regression, the fit with those values. So you can see it's already not too bad. You know, it's not quite getting these values here, it's not quite getting those values there. So obviously it's not quite what we want it to be. But it seems like perfectly plausible starting values. Okay, so now I need to actually, let me go back to this and say one thing, which is, if you go back to what we were talking about at the start of class, what am I doing here that's really kind of stupid with this particular problem here? What's the hard part of this problem and what's the easy part of the problem? Well, that could be hard. That's sort of a different hard than I was trying to get at. We're just talking about profiling, right? Why is that relevant here? If you give me beta 2, I know beta 0 and beta 1 in closed form as the regression estimate, as the OLS estimators, right? So I can profile beta 0 and beta 1 out of this problem and just do the maximization for beta 2. Okay, so I'm not doing that here for the sake of illustration, but if you were really solving this problem, then that would presumably be what you wanted to do. Okay, so let's continue on where we're just numerically minimizing with respect to all three of these, even though we recognize that we could have done the profiling and just had a univariate problem. Okay, so Kelly was asking, how hard is the differentiation? Maybe that's something we need to be careful about. So what I've actually done here is, instead of trying to do these derivatives by hand, I already told you last week that whenever I take a derivative, I always make a mistake. So it would be good if I could have the computer take my derivatives for me. So you can actually, if you basically write out. Okay, so the objective function in this case, this is just a nonlinear least squares problem. The objective function is just a sum of squares. So I'm going to write out a little R expression using quote. Remember this from when we were talking about not having R evaluate code, but just sort of put it into a symbolic form. I'm just going to write out weight minus beta 0 plus beta 1. So this is just the sum of squares, which is just the objective function here. And I'm going to store that in an R object that I'm calling expression. And R has a bit of symbolic differentiation ability, so I can actually take the derivative of that expression object with respect to beta 0, beta 1, and beta 2. And I can also take the second derivative by calling this deriv3 function, and that will, by default, give me the Hessian as well, the matrix of second derivatives. So it's going to give them to me in symbolic form. It'll have done the symbolic differentiation for me, and that will hopefully save me from making differentiation errors. You could also do this in Mathematica or other kinds of software. And if you're doing more complicated problems, you'd probably want to use something other than R, but R can handle some symbolic differentiation. Okay, so once I do that, you can see that it spits out sort of an ugly result that has in it a whole bunch of these partial objects here that are basically from doing partial derivatives of pieces of the expression. And then the resulting, say, gradient and Hessian comes from, like here are sort of pieces of the Hessian that come from combining together these sort of partial expressions that we calculated earlier on. So I don't want to sort of go into the details too much of that. But you can basically pull out the symbolic derivatives from the result here that R gives back to us. And R wouldn't have dealt with taking the sum over all of the observations, so I have to do a little bit of post-processing of manipulation of what I get out of from having done the symbolic differentiation in R. But once I do that, I can create an f prime, a gradient function, that for a given set of betas will calculate the gradient, and it looks something like that. So it's these sort of sums over these partial expressions, and those partial expressions come from having done the symbolic differentiation. And then I can also create an FPP, an F prime prime or Hessian function that will calculate the Hessian for a given set of betas. And that's going to return a 3x3 matrix, so I'm just filling in the elements of the matrix here. Okay, so now once I've got those functions, I can now set up my Newton's method for this particular problem. I'm not going to deal with sort of convergence diagnostics or anything. I'm just going to run this flat out for 20 iterations and assume that it's going to converge after that, although we'll look at it. But I'm just going to set up a matrix that will store the values of the betas at each of the iterations. I'm pre-allocating that for the reasons that we talked about in Unit 4. And then my first row is just going to be those initial values that I'm starting with that we already discussed how we came up with those. Okay, so questions so far? Comments? Okay, so here's me just coding up in R Newton's method. The value at the tth iteration is the value at the t minus 1th iteration minus, and then I've got my FPP that's going to calculate my Hessian. I'm going to do solve of that comma and then the gradient factor, so it's going to solve this implied system of equations. And that's going to give me my Newton update, which will give me the next iteration's values for beta. So I had a little bit in here that I was playing around with, well, what happens if I do find that I can't do that, that I don't have a numerically positive definite Hessian? And I was playing around with the pseudo-inverse. It turns out not to be needed in here, so I don't actually use the code here. Okay, so now if I look at what x values are, we can see that I started out at 99, 87, and 100. Remember the 100 came from the beta 2. And now if I look after a few iterations, we can see it's converging pretty quickly. It looks like it's basically converged to something that's pretty stable by the time of the 6th or 7th iteration here. So it didn't take very long to converge in this case. What am I doing here? I guess if I... Okay, it turns out R has a nonlinear least squares optimizer already built in, and so you can just put in the equation the formula that represents the model that you're fitting. And it also requires starting values, so it doesn't get you away from this problem of thinking about starting values. But if we run it, we should see that we're going to get the same answer as we got before. So the answer was 81.37, 102.68, 141.91. You can see those are the same values that it spits out from showing the results of the optimization here. And I suspect these are the values of the objective function at each of the iterations, and then these are the parameter values. So it looks like it's reporting that it's converged after about 5 iterations. I don't remember exactly what method it uses, but it's something closely related to Newton's method. It's probably not exactly Newton's method, but something similar. Okay, and if we go ahead and just take, we can then go ahead and just plot the fitted values and see if we've done pretty well. In this case, it looks like this model fits quite well to the data. The blue curve pretty much goes sort of straight through most of the observations. Okay, any questions about that? All right, so the next thing I want to talk about is just a couple sort of standard optimization methods that are used for statistical models, in particular for likelihood-based estimation. And I just wanted to show that they're basically very closely related to Newton's method. So the first of these is something called Fischer scoring. So those of you who were in 201A and 201B, have you encountered and talked about the information matrix so far? Yeah, okay, so this should be familiar to you. So the information matrix is taking the gradient, f of y is the log likelihood, taking the gradient of the log likelihood, the outer product of that, and then taking the expected value with respect to the data distribution. So this thing is going to be a function of the parameters and the data, but once I take the expectation, I'm taking the expectation over the observations. So the stochasticity from the observations is integrated out by virtue of that expectation. So now I have this information matrix that's a function of theta. So under what we call regularity conditions, which is conditions on the structure of the model, and this is true for any exponential family like normal distributions, Poisson distributions, binomial distributions, a lot of standard distributions, this information matrix can also be written as the negative. I'm just moving the negative over here. The information matrix is also the negative of the expected value of the Hessian, of the matrix of second derivatives. Okay? So that under this regularity conditions, this thing is the same as this thing except with a minus sign there. Okay, so the idea of what Fischer scoring is, as opposed to doing Newton-Raphson, is for Newton-Raphson we had the Hessian matrix, and that was used in determining our next update. We had the minus of the Hessian inverse times the gradient vector. The idea of Fischer scoring is instead we plug in for the Hessian, we plug in the expected value of the Hessian, which is minus the information. Okay? And so it's really just changing that matrix that gets used in Newton-Raphson. So basically what ends up happening is it doesn't in Newton-Raphson we have theta t plus 1 as theta t minus hf of theta t inverse times the gradient. And in Fischer scoring we have theta t plus 1 is theta t, and now there's going to be a plus because of the minus up there. The information matrix okay, so sort of lots of words floating around for different kinds of methods, but at its core, if you think you understand what Newton-Raphson is doing, you basically understand what Fischer scoring is doing. It's just using a different matrix in here. And you're sort of averaging, I don't have a great intuition for this, but you're sort of averaging over the variability that would come from getting the particular draw of the data that you got compared to other data draws that you might have gotten if you reran the experiment. So both of these have quadratic convergence. In sort of different problems, one or the other might converge more quickly, but there's not a huge difference between the two of them. And I have an example in the code here, in the R code, where I basically say, well, okay, the only thing I need to do to change Newton-Raphson to Fischer scoring for this problem is I need to take my Hessian matrix and take expectations. And so in my original FPP function, which was calculating my Hessian for this weight loss example, I had all of those sort of these sort of partial expressions that when combined together would give me the Hessian. only a few of these, it turns out, are functions of the data, and in all cases, you just have linear functions of the data, so the expectation just carries through really easily. So I was able to convert my Hessian to the information matrix-based version really easily, and just come up with a new function that would do Fischer scoring instead of Newton-Raphson. So then all I did was I changed my updating to use this FPPFS, which does Fischer scoring by calculating the information matrix, instead of doing just the straight Hessian matrix. Minus, oh yeah, so I guess there should be a plus. What probably happened, I think this code runs fine. I think what happened was I probably have another minus in the original FPP that cancels out with this minus, but yeah, that would be a good catch. I'd need to make sure and check on that. So there's a possibility there's a typo here. So I don't think I'll bother running that because you'll just see sort of similar things to what we already saw before. Okay. Oh, I see. So yeah, so nonlinear least squares, I actually did have a note on this. So when I ran the NLS function to do the nonlinear least squares for the weight loss example, it turns out if you look into the help information, it uses the Fischer information rather than Hessian, and it gives a Newton-like step instead of precisely a Newton-Raphson update. And we'll see what I mean more precisely by a Newton-like step probably next time. But that's something called Gauss-Newton, so it seems like if you take all combinations of famous mathematicians and statisticians, you get sort of different variations on these optimization algorithms, but they're all very closely related. Okay. Any questions about that? Okay, the other thing I wanted to comment on here, when I've sort of made a comment like this before when we were talking about regression and numerical precision, which is what are the cases when we would see that the Hessian matrix was not positive definite? Okay. So if we're thinking about, we're trying to minimize something, and I'm at some point in this, say I'm thinking of some sort of bowl, and I'm trying to find the minimum in that sort of high-dimensional bowl. The Hessian is basically giving me sort of the quadratic behavior of where in terms of where I am in that bowl. And it might be the case that I'm in a very flat space, a very flat spot in doing the minimization. So I might, for example, in two-dimensional space, be something. I might have a case where I have something like this, and let me draw it even more extreme. That in this direction, the gradient is fairly large, but in this direction, the gradient is very, very shallow. And if I think about what that means from a statistical perspective, it means I don't have a lot of information in the data that says that this value is better than this value is better than this value, but I do have a lot of information in the data that says this value is better than this value is better than that value because of thinking about the contours of the function that the objective function that we're optimizing here. So oftentimes the cases where you're going to have problems with positive definiteness of the Hessian matrix is in cases like this where you have very shallow, it's very shallow in one or more of the directions. And so if that's the case, this idea of having the numerical problem of not having a positive definite Hessian sort of goes hand in hand with the statistical issue that you don't have a lot of information in at least one of the directions about the parameters that you're interested in. So that's something to keep in mind if you're doing optimization and you're having trouble with things being very shallow or having the Hessian be not positive definite. Okay. So let's see. I guess the last thing I want to talk about today is iteratively reweighted least squares for GLMs. Okay, so I'm not sure where you guys are in 201B, those of you who are taking that, or even whether you talk about GLMs and iteratively reweighted least squares. So how many people have at least had a passing glimpse of how to fit generalized linear models with iteratively reweighted least squares? Well, is it just my pronunciation that was so bad? How many people are familiar with it? Just a couple of you? Okay. Okay, so I don't want to sort of work through a full derivation of this, but I just want to do enough to basically show you that iteratively reweighted least squares is just Newton-Raphson. It's just doing a Newton update to estimate the parameters of a GLM. Okay, so those of you who've seen iteratively reweighted least squares will know that what we do is basically we solve a weighted least squares problem where we get the beta hats as a function of a weight matrix, our original x covariate matrix, and a vector of y's, which are not the actual observations but are what are called working observations. So the idea is that at each iteration, the weight matrix is basically a diagonal matrix that has the variances of the observations. And the y's are the observations on basically what's called a linearized scale. So they're basically the predictions. Whenever you do a generalized linear model, there's a transformation. There's a logistic link in logistic regression. There's an exponential link in Poisson regression. What this y ends up being in weighted least squares is basically the y, but sort of on the scale of the betas. So if we think about what, we take an example of like Poisson regression. What's the standard Poisson regression? It's that y is Poisson. So yi is Poisson, xi, sorry, it's not the standard Poisson regression. So that's the standard Poisson regression. These are the linear predictors. We have a link function that basically transforms from the scale of the linear predictors to the scale of the observations, which are the y's. And the idea of the y up there is that I should have used a different notation. That's not actually the same y up in the equation here. This is supposed to be this working observation, the working y's. And the working y's are basically a version of the y's that are sort of on the scale of the x betas. And so the idea is if you put the y's sort of on the scale of the x betas, you can get an update of your beta hats that looks like this, which is just a weighted least squares problem. That new value of beta is basically the next value of beta in an iterative procedure, and then you recalculate the working y's and the w's with your new value of beta, and you solve this again, and you do iterations, and it converges to the maximum likelihood estimator. Okay, so the standard way that people will write out an exponential family, which would be a normal model or a Poisson model or a binomial model or related models, is you can sort of write it out in this notation here. And they all look like this with particular values of this function b and of this function a and of that function c. And this theta in the standard setting is just equal to what's called the linear predictor, and usually if we're just fitting a usual regression, then eta is just x beta. So what you can do when you've written it like this is basically if you plug in x beta for theta here, and you take a log to get to the log likelihood, and now you think about writing down what the gradient is with respect to beta and what the Hessian is with respect to beta, what you get is that the gradient looks like y minus e of y transpose times the x matrix, and the Hessian looks like minus x transpose wx, where the w's, as I said a minute ago, were a diagonal matrix with the variance of the y's on the diagonal. So those variances in our Poisson setting are, since the variance is the same as a mean for a Poisson distribution, those variances are basically just exp of xi theta. So this is going to be the value wii in our weight matrix. And then the e of y I is just going to be exp of xi transpose beta. So this would be the Poisson setting. And you can work out similar sorts of things for if you were doing logistic regression, and therefore if you had a binomial distribution for the y's. Okay, so if we're sort of approaching this from the perspective, okay, suppose you're willing to bear with me for the fact that I've been sort of vague in this quote unquote derivation, and I've just asked you to believe me that I can take the gradient and Hessian and I get these values. Well, now if I think about doing Newton-Raphson or Newton's method in this particular context, what does it look like? Well, it just says the next value of beta at the t+1th iteration is the current value plus the inverse of the Hessian, which we just said was this guy. Well, it would be minus the inverse of the Hessian, but I've got a minus and a minus, so I've got a plus. So plus the Hessian inverse times the gradient vector, which in this case, just to make sure that I've got the things as a column vector instead of what looks like here with the row vector, the transpose of this, so I have x transpose y minus e of yt. And these guys, as we see in the Poisson example, are both functions of beta, so there'd be a beta t in here. I would need to know the current value of beta to be able to calculate what each of these guys was. Okay, so the idea then with seeing that that what I just wrote there as Newton's method is the same as iteratively reweighted least squares is there's just a simple algebraic manipulation that will show that. So if I take that guy, okay. Did I miss something here? Why? Oh, I do need parentheses, right? Thank you. Great. Part of my brain apparently realized I needed it, and part of it didn't. Okay, so I want to make this look like this, which is the standard, iteratively reweighted way of writing iteratively reweighted least squares, which is also called iteratively weighted least squares. And if I look at this and I look at that, well, one thing I might think about doing is taking the beta t and basically multiplying by the inverse and by the non-inverse of this matrix. So I could write this out. I could write this as being equal to x transpose wt x inverse x transpose wt x times beta t plus this stuff I had up here, which is x transpose wt x inverse x transpose y minus e of y. And now if I pull out my x transpose x, x transpose w, t x inverse, what I will get is that there's an x transpose w t, so you can see there's an x transpose w t here, there's an x here, and I'm going to put in a w and a minus w to cancel out here. And I can get this as x beta t plus wt inverse y minus e of y t. Let's see if we get that right. Okay. So if I look at this, well, this is just weighted least squares with this new thing here, which I'm going to call wy tilde t. So this is what I should have written as y, what I had as y originally further up here. This is my working observation, set of working observations. And what is it? It's basically the fitted values on the scale of the x betas plus a sort of reweighted version of the residuals from the model. So these are the original data. These are the fitted values, so these are residuals. But then I sort of do some weighting to get them sort of onto the same scale as the x betas on the scale of the linear predictor. So we're basically out of time, and I don't have too much more to say about it than that, except just that, again, this idea of part of what I want to do here is draw these connections between these different methods so that when you see iteratively reweighted least squares and you also know about Newton's method, it's not like these are totally distinct things and like there's so many different kinds of optimization methods going on. What's going on is there are these tight connections between them, and you can just derive this as doing Newton's method. And it's just sort of a convenient re-expression that makes it look like a standard weighted least squares kind of problem. Okay, so that is the standard method for working with GLMs. And so next time we'll continue on in this theme of talking about a few other of these different kinds of optimization methods in higher dimensional spaces.